Hey guys, this is Mrs. Cribb, and this is a review video for Test 10. I just wrote down a few things that you need to remember. One of them is to review your terms. You need to spend time on the Quizlet in order to do that. So we're going to take a moment to go to the Quizlet. Here is the Prezi. You can use that to look at the pictures and all. And here's the Quizlet link. So just click on the Quizlet link and it'll pull it up. And there's about 26 terms. Yeah, 26 terms for you to look at. And so you need to kind of go through them. Use your flashcards. I just was playing around with it earlier. You know, look at all the different things. What held Charles' law? Let's see, what's that? Yeah. What's held constant in Charles' law? Yada, yada, yada. Let's see. Diffusion of gases. Let's see that one. And it's just showing you before and after how we have the concentrated area diffuses through. Collected by water displacement, and what it means is the gas is bubbled up through the water and collected up here, and inside there will be the water and the gas, and so remember you have to subtract out the water vapor. Effusion, going through a little hole, moving through the hole. The relationship between pressure and volume, and just showing you here Boyle's law and how we have a greater pressure and the volume goes down. What do you need to do when you want the pressure of a dry gas but it's collected over water? You got to subtract the water vapor. Gases movement just shows you how gas move around randomly in different speeds. Charles' law, what's the R stand for? And this just gets to give you different variables. Same variable but different values for the R gas law constant. What is standard temperature and pressure? Boyle's law, ideal gas law, molar volume, gases flow and R. Fluids, and this is showing you one gas that can be poured out. Just stoichiometry, the pathway that we use. This is just like the one I do. Sorry. Elastic collisions. This is just showing you how when they collide and they go away, that the sum, the 1 plus the 2 is still the same. The sum of the energy is the same. So that's elastic collisions. Dalton's law of partial pressures, easy one. Combined gas law. I'm just kind of going through them quickly to see which ones I wanted to show you. But anyway, go back through them and make sure you spend plenty of time on these things contained within the Prezi. I did not assign this, but even general chemistry, you need to make sure you spend time doing this because those terms will be on the test. And you need to make sure you understand it. Okay? That is the reference sheet that we're going to be using, and I'm going to refer to that while we go through some of the questions. So there we are. We went through that. Go through all your targets. The targets have been given to you. If not, you can get them off the Google Drive folder and review all calculations. And so we're going to go through the calculations now. Practice problems. Now you can print this out if you want to. In fact, I'll put it on the Google Drive folder so you can use it to look at if you're practicing or you want to review a little bit more. But we're going to go through here and mark this all up. So I have a balloon that holds 350 milliliters. That's a volume of air at a room temperature of 25 degrees Celsius. That's the temperature. And if I put it in the freezer, a new temperature, what will its new volume be? Okay, so we're going to use Charles' law. Now, I put this in parentheses just because when I was making it, I'd make sure I was covering them all. But how would I know that I'm using Charles' law here? Well, I would notice that I have volumes and temperatures. And so if I go and look at my reference sheet, volumes and temperatures are right here. I'm going to use this particular gas law, V1 over T1, and that is called Charles' law, and you need to know that. So I highly, highly recommend that you put all your variables off to the side. So what the first volume was 350 milliliters. The first temperature is 25 degrees Celsius. V2 is my question right here. And T2 is 5 degrees Celsius. Now the first thing we always have to remember is we have to convert to kelvins. All the temperatures have to be converted to kelvins. So we're going to add 273 to both of these temperatures to get kelvins. Remember, why do we convert to kelvins? Because we can't divide by 0. All right, so here I have converted both of these to kelvins. And now I'm going to write the formula V1 over T1 equals V2 over T2. And remember that this, writing this formula right here is a point. Identifying the formula is a point. And then I'm going to put the values into the formula. So V1 is first, so 350 milliliters over T1, 298. Now you notice how I mark it up. This is so I'm keeping track and making sure I'm putting everything in the right spots. Please don't be lazy and neglect to do this kind of thing. It's important to use these skills to keep yourself straight, because I still make mistakes doing this. All right, once I do this, how do you solve it? You cross multiply. So remember, you need to cross multiply to solve. It's super important. Otherwise, you'll divide by the wrong number. So when you cross multiply, you take the numerator of one and multiply it by the denominator of the other side. So we're going to have 298 kelvins times V2, and then this one, 350 mils times 278 kelvins. And then I want to isolate the variable. So I'm going to divide both sides by 298 kelvins in order to be able to cancel out the kelvins on this side and the 298. And over here, just the unit Kelvin cancels out. So now I have 350 times 278 divided by 298. I'll pull up my calculator for you this time. I'm not going to do it every time, but 350 times 278 and the divide by 298. And I got 326.5, so V2 is 326.5. I put more significant figures there than I need. So I need to figure out how many significant figures. Well, remember the significant figures are, you count them when you're multiplying and dividing, and you use the smallest number. So this only has 2 sig figs, so my answer can only have 2. So I've got to round to this spot. So that rounds to 330, and the unit is milliliters, and that's the answer to the first question. Now let's think about this for a moment. What's the relationship between volume and temperature? If the pressure is held constant, so in Charles' law, the pressure is constant. The pressure does not change. Okay, so, excuse me, the temperature goes from 298 to 278. So the temperature went down. When the temperature goes down, the volume should go down. Because with Charles' law, when the volume goes up, it's because the temperature went up. Think about our experiment when we use with the syringes. When the temperature goes down, the volume goes down. So the temperature went down from 298 to 278. The volume went from 350 to 330. So that was good. It followed the same relationship. Let's go to the next one. The pressure of a helium, of a sample of helium in a 1 liter container volume is 0.988 atmospheres pressure. What will the pressure be in torr? So that's P2, and they also want it in torr if the sample is put in a 2 liter. So that's a new volume. Okay? All right, so this is Boyle's law because it only contains pressures and volumes. I can know by look at my reference sheet, P1 V1 equals P2 V2. That's the only thing I have, so that's what I'm going to use here. So first I'm going to list my variables. We have volume 1. My volume 1 is 1.0 liters. My pressure 1 is 0.988 atmospheres. Volume 2 is 2.0 liters. And pressure 2 is my unknown. Now, they want us to give the pressure in torr, and there's 2 ways to do that. I could change these atmospheres to torr initially, or I could calculate for the pressure and then turn it to torr. So I'm going to do it the second way this time. Okay? So P1 V1 equals P2 V2. That is that thing you have to do for 1 point. Now, let's fill it in. P1 0.988 atmospheres times V1, 1 liter, is P2, which is my unknown, times 2.0 liters, my V2. Okay, now we're going to divide both sides by V2, or the 2.0 liters. going to cancel out liters on the denominator rather, and the numerator. And so now it's just going to be 0.988 divided by 2. And so the second pressure is 0.494 liters. And then I check sig figs. Always check sig figs. And if I look at my significant figures this time, 1.0 has 2 significant figures, so does 2.0. So I need 2 sig figs. Leading zeros are losers, so it's 0.49. I have to round to that spot, 0.49. But what's the unit? Atmospheres. Okay, but the question is not atmospheres, it's torr. So now I got to convert. And so you've got to remember how to convert. So I take my 0.49 atmospheres, and I'm going to convert it. 1 atmosphere is equal to how many torr? Well, you don't have to guess. You just go back to the reference sheet. Here's 1 atmosphere is equal to all of these things, so I can set up any kind of conversion factor. 1 atmosphere equals 760 torr. Okay? So 760 torr goes on top. I cancel out my 1 atmosphere. And so now my new pressure is 372.4, and I look only 2 significant figures, 2 sig figs, so 370 torr. That's my final answer. Okay, so this question would have had several possibilities of probably a 3-point question, 1 for this, 1 for the first answer, and 1 for the converted answer. So make sure you're very careful about all that. All right. So that's Boyle's law. Has nothing to do with temperature. Let's go now to Gay-Lussac's law, or Guy-Lussac, or whatever. And I just kind of didn't want to write the whole thing as I was working this out. Okay, so helium gas in a 5-liter cylinder, that's a volume unit, is under a 450.3 torr pressure. That's obviously a pressure unit. At 43.7 degrees Celsius, that's a temperature. The same sample of gas, all right, that's important. The same sample of gas has a pressure of 120.3 kilopascals. That's another pressure. What was the original temperature, okay, of the gas in the cylinder in degrees Celsius? It's also asking me for a certain unit. All right, since it's the same pressure, the same sample, the volume's not changing here. The volume stayed the same. It doesn't even give me a second volume option. So it has 2 pressures, it has 2 temperatures, but only 1 volume. The volume stayed the same. So if I go back and look, pressures and temperatures only is this right here. P1 over T1 equals P2 over T2. The volume stays the same. So that's what happens with this law. The volume stays the same. Here the volume is the same. And that's important, an important aspect of Gay-Lussac's law. Just like in Boyle's law, the temperature is the same. And that's an important aspect of Boyle's law. In Charles' law, the pressure doesn't change. So you see, you got to know what changes for each law. All right, the volume stays the same. So let's write out the P1 and all that, okay? So P1, first pressure is 450.3 torr. And the T1 is 43.7 degrees Celsius. Is that right? I don't think I read that right. Helium gas in a 5-liter cylinder is under a pressure of this. At 40 degrees Celsius, the same sample is under a pressure of 120.3. So no, this is not the first temperature. I also know because it says what was the original temperature. That would be T1. So in this case, I'm actually going to be looking for T1. So T1 is going to be my question. So what is P2, the second pressure? Well, it says at this new temperature here, 43.7 degrees, the same sample of gas is 120.3 kilopascals. So that's my second pressure. I know. Again, I've got to convert my temperatures to Kelvin. So I add 273 and I get 316.7. And these are the correct sig figs. When you're adding, you do look at place value. But 273 is a definition, and so the place value is going to come from the original number. We're not going to lose that 0.7 this time, okay? So we keep it there. All right, now we can solve P1 over T1 is P2 over T2. Remember, you have to write the formula because that's a point. We put the values in. P1 is 450.3 torr. T1 is my unknown. P2 is 120.3 kilopascals. And T2 is 316.7 kelvins. Okay, we got to solve by cross multiplying again. So T1 times 120.3 kilopascals equals 450.3 torr times, because I'm doing this way, 316.7 kelvins. All right, now we're going to divide by 120.3 kilopascals. Well, now I've just noticed a new problem. Do you see it? My torr and my kilopascals can't cancel. That means one of them needs to change. So since the 120.3 is on the bottom, I'm going to change that one. I could have changed 450.3 torr to kilopascals or 120.3 kilopascals to torr, but I got to change one of them so the units will cancel. So we're going to change 120.3 kilopascals, and I'm going to change it to torr. So there's 760 torr and some number of kilopascals. So I go back to my reference sheet. Here's the relationship. 760 torr equals 101.3 kilopascals. So there's the relationship I'm using right there. So 101.3 kilopascals. Cancel the units, kilopascals and kilopascals. And when I multiply those, I get, I'm going to double check this math just to be sure. Let's pull up the calculator. 120.3 times 760 divided by 101.3, 902.546. Okay, good. 902.546. Then there are 4 sig figs, so 1, 2, 3, 4. So 902.5 torr. All right, that's what I need to use. I need to cross that out and use 902.5 torr. Okay, now, because of that, now I can cancel out torr and torr. And I can do this math and figure out what T1 is. Okay, so 450.3 times 316.7 divided by 902.5, and I get 158.016, and then I check for significant figures, and everything has 4 sig figs, so 1, 2, 3, 4, so 158.0 kelvins. That's my temperature. Okay, well that's awesome, but the question didn't ask me for kelvins. Asked me for degrees Celsius. So I got a little bit more work to do, not much. All right, remember that kelvins is equal to Celsius plus 273. We've been using that right here. We used it to convert to kelvins. And that means that Celsius is equal to kelvins minus 273. So I'm just going to say 158.0 minus 273. And I get a negative 115.0 degrees Celsius. That's a perfectly legitimate number. It has to keep the decimal because 273 again is the definition. So this is the correct answer in the correct units. Be careful that you make sure you have the significant figures and your units cared for or taken care of. All right, let's move on. Number 4. I did this question mostly because I want to find questions that are kind of interesting, and this one is going to require stoichiometry. So before we do it, I'm going to write out the stoichiometric pathway for you again. So moles of A go to moles of B using the molar ratio. You should know that. Mass of A goes to moles of A using the molar mass of A. Moles of B goes to mass of B using the molar mass of B. Molecules of A, molecules or atoms, goes to moles using Avogadro's number. Moles can turn into molecules of B using Avogadro's number. And now we have the new one, volume. Volume of A goes to moles of A using the molar volume. Moles of B goes to volume of B using the molar volume. What's the molar volume? The molar volume is 22.4 liters are in 1 mole. Or the other way around, 1 mole is 22.4 liters. That's one thing that's not on the reference sheet. There's nowhere on there is molar volume. If you can't remember it, you could put that on your 4x6 card. All right, I'm going to do this because I'm going to ask a lot of questions about this, okay? So hydrogen cyanide is a poisonous gas that was used in the gas chambers during World War II. It can be formed by this reaction. Now, notice this has some ions in it. Don't worry about that. Say, what mass of sodium cyanide? So the question is asking for mass. And so that's going to be my B. Is required to make 14.7 liters of hydrogen cyanide. The thing that I know about is my A. At STP, and that's important because molar volume can only be used at STP, at standard temperature and pressure, and you need to know what those are. So what is the standard temperature? The standard temperature is 0 degrees Celsius or 273 kelvins. You need to know that. I did not put that on the reference sheet, and I want you to memorize it. What's standard pressure? 1 atmosphere, or anything that equals 1 atmosphere, which again, if you look at your reference sheet, that means all of these things are standard pressure. So only when we have standard temperature and pressure can we use this molar volume in our calculations. All right, so we're going to do this. We got to figure out where we're starting. We're at liters of A, so that means we're starting here at the volume of A. And I want to get to the mass of B. So this is the path I have to go from volume to moles. So I'm going to start with what I know. 14.7.7. I didn't write that down. 14.7.7. So 14.7. Let me erase that so we can. Wow, that's a highlighter. Let me erase that. Okay, there we go. 14.7 liters. There we go, of hydrogen cyanide. First thing I need to use is the molar volume. Okay, I'm going to turn it into moles. I'm headed towards moles, so I know I want moles on top. And the liters need to cancel. Cancel my unit, liters and liters. So that's the first step. I use the molar volume. Now I'm going to go from moles of A to moles of B using the ratio, which is B over A. Now this time, the ratios are 1 and 1. One of those and one of those. Remember the ratio numbers. The ratios come from the coefficients. The ratio only comes from the coefficient in the balanced equation. This equation is already balanced. The ratios come from the coefficient. So B is this one. We get 1 mole of sodium cyanide for 1 mole of hydrogen cyanide. All right, now let's cancel our units. Hydrogen cyanide cancels. Moles cancel, and so I have moles of sodium cyanide, and which is one of the questions is moles, but we're going to come back to that in a minute. All right, what's the next step? All right, I need to get to mass, so I've got to figure out the molar mass of molecule B. That's molecule B, sodium cyanide. So I'm going to calculate the molar mass of sodium cyanide. I'm going to do it over here real quick. Sodium cyanide. So I need a sodium, a carbon, and a nitrogen. And you get these numbers, 22.99. This comes from your periodic chart. It's not 23.00. The number is 22.989. In fact, I'm going to look at the chart real quick to see. 22.989. Right. And I told you to give me 2 decimal places. So that's right there. So that 9 causes it to round up. So 22.99. 12.01 for carbon and 14.01 for nitrogen. All of these come from your periodic chart that I've given you. Now, I don't have to multiply these by any number because you look at only the molecule not the coefficient. Even if the, if it was a 2 H2s plus O2, if you want the molar mass of hydrogen, it's H2, not 2 H2s. It's not 4 hydrogens, it's just 2 of them. You do not look at the coefficients for molar mass. In this case, there's only one anyway. You add it all up together, and I get 49.01 grams per mole. You need to put the unit and the 2 decimal places so you don't lose any significant figures. And so that's the molar mass of molecule B. All right, 49.01 grams in 1 mole. Now I can cancel out units again. Moles and moles cancel. And I end up with 32.16. And I look at significant figures. The beginning number has only 3 sig figs, so I need 3. That 1 needs to be rounded because we're going to round to that spot. So it's 32.2 grams of sodium cyanide. Okay, that's the first question. Now I ask you several other questions. How many molecules is that? Well, that's the Avogadro's number thing. So right now I have mass of A. I have a mass of something and I turn it into molecules. I can turn mass to molecules, but I have to go through moles. Okay? So you can turn mass to moles to molecules because we're changing it into the same thing. All right. 32.2. Okay. I'm trying to figure out where I am on my own paper. All right, so 32.2 grams of sodium cyanide. I'm going to turn it into moles using the molar mass of sodium cyanide, which I already calculated. So 1 mole is 49.01 grams. And then I'm going to go ahead and cancel that unit, gram and gram. And then I'm going to need Avogadro's number to turn it into molecules. So 6.022 times 10 to the 23rd molecules are in 1 mole. It's not grams in a mole, and it's not grams in a molecule. It's that many molecules are in 1 mole. Cancel out moles. And we're going to put it all in a calculator this time so we can see it all. All right, 32.2 divided by 49.01, and then I'm going to multiply it by 6.022. There's the second function in the double E 23. Enter. Okay, so it gives me 3.95 or 956. Hold on one second. 3.956, and we need to make sure we have this E23 in our answer. A lot of people are forgetting that when they're doing it. Be careful to add that to your answer. It's times 10 to the 23rd. So this is 3.956, and now I look for significant figures. It's going to be times 10 to the 23rd, but I need to look at sig figs. There are 3 sig figs here, so I have to do 1, 2, 3 sig figs. That has to round up. So 3.96 times 10 to the 23rd molecules of sodium cyanide. All right, that's the molecule answer. Okay, I just did that one. How many moles? All right, well, I just need to turn it into moles then, so I could do this same calculation and not add that part. So 32.2 grams of sodium cyanide. I already know the molar mass, 49.01 grams, and I'll be able to turn it into moles. Now, where would that be on the chart? Well, I'm starting with mass, and I'm going to moles, and I'm going to use the molar mass. It's just one step. Okay, so 32.2 divided by 49. 32.2 divided by 49.01, and I get 0.6570. 0.6570. 3 significant figures, 1, 2, 3. Leading zeros are losers, so 0.657 moles, 0.657 moles. Okay? Now, let's see, that gives me this answer. And I have to do liters. How many liters is it? Well, how would I do it on this chart this time? If I'm starting with mass, and I want to go to liters of A, I have to go from mass to moles, and then from moles to volume. So see, I'm not changing molecules, so I'm never using a ratio this time. I'm just moving around inside this path. So 32.2 grams of sodium cyanide. Turn it to moles. 1 mole over 49.01 grams, because I already know what that is, the molar mass right there. And then grams cancel. And then 22.4 liters are in 1 mole. And why can I use that? Because it's already at STP. Moles cancel. And so now do this one on my calculator. Oops, missed it over. There we go. 32.2 divided by 49.01 times 22.4, and I get 14.16 really. And then if I look at this 3 sig fig, so 14.2 liters. 14.2 liters. Is that the right answer? I'm going to make sure I didn't. 14.716. Ugh, I didn't write the right answer. So it's 14.716. Oh, whoop, there I am. So it's 14.716. It's 14.7 liters. I just didn't copy it down right when I wrote it down. Be careful about that too. Transcription errors can cause you issues. All right. Hopefully you understood that one. I just did that one because I want you to see that you can use this pathway to go from any spot that you need to go through. Just figure out where you're starting and stopping. And this time I never went to a new molecule for those last 3. So I never had to use the ratio. The ratio is only when you're changing the molecule. All right. I'm going to pause for just a second. I brought up the next question for you. Calculate the temperature of a 969 milliliter, that's a volume, sample of methane gas at 104 kilopascals. It's a pressure. It has a mass of 0.647 grams, so it's not a whole lot. It's a tiny little bit. So what can I use? Well, this one says use the ideal gas law. How did I know that? Well, I know that because it's asking for temperature. It has 1 pressure, 1 volume, 1 temperature. And if I look at the PV equals nRT, what do I have? I have a pressure, a volume, a temperature. I don't have the R, but I always get the R. So can I get the N? Well, I can, because what does N stand for? N is the number of moles. Okay? I don't have the number of moles, but I do have the mass, and I can turn mass into moles because I have to just use the molar mass. Remember, the mass of A can be turned into the moles of A using the molar mass of A. So that's what I'm going to start off by doing. I take 0.647 grams of methane and CH4 and 1 mole. And so I just need to know the molar mass of methane. Okay, so let me calculate the molar mass of methane. 1 carbon is 12.01. 4 hydrogens, that's going to be 4.04. All right, when I add those two together, those two, I get 16.05 grams per mole. That's the molar mass. Now, this is going to be a small amount. This is not going to be a big number of moles. In fact, I'm going to go ahead and do this one on the calculator just so you can see. So 0.647 divided by 16.05, I get 0.040311. Let's write that all down. 0.040311. All right, let's look at sig figs. Leading zeros are losers. 1, 2, 3 sig figs. Leading zeros are losers. 1, 2, 3 sig figs. So it's a 0.0403 moles. Now that's my N. So now I have my N. So I have all the things I need for PV equals nRT. So PV equals nRT. Okay. Now this question I'm going to tell you is going to be a little more involved than the ones I'll put on the test. But it'd be a good one to make sure you understand, or maybe to write in on your sheet, because on your card, your 4x6 card, because it kind of demonstrates a lot of different things. All right, so the pressure is 104 kilopascals, and the volume is 969 milliliters. N is 0.0403 moles. R I got to figure out, and the question is calculate the temperature, so T is my unknown. All right, so I got to figure out which R to use. Okay, I don't know. I always have to look. So I'm going to go to my reference sheet, and my R values don't have, let's see what units I have here. I have kilopascals and milliliters. My R values do not have kilopascals, they have pascals. And they don't have milliliters, they have liters. So I've got to convert some things so that I can use one of these R values. So this time I'm going to use my liters, and I'm going to have to convert to liters and to torr. I'm going to convert my milliliters to liters and my kilopascals to torr, and then I'll be able to use this R value. Now that's a little bit more complicated than you normally do, but I wanted to show you that it's possible, okay? So please follow along. All right, so instead of using kilopascals, I'm going to convert those to torr. So 104 kilopascals. There are 760 torr in how many kilopascals? That's my first thing. So I go and look on my reference sheet. 760 torr in 101.3 kilopascals. There's my relationship right there. So 101.3 kilopascals. Now you can see the units cancel, and if I multiply those through, I get 780 torr in a decimal place, torr. I have to have 3 significant figures. Okay, so I'm going to change this number from 104 kilopascals to 780 decimal place torr. I almost write kilopascals again. Let's erase that. Wow, made a mess, didn't I? 780 dot torr, and that one went away. Okay, that was my first conversion. And then milliliters needs to turn to liters, so that's easy. 969 milliliters. There are 1 liter is 1,000 milliliters. You need to know this by now. So that's just moving it to the left 3 places. 0.969 liters. So I'm going to now cancel out the milliliters and put 0.969 liters. So now I've got liters and torr. Now can I use an R value now? Liters and torr, moles and Kelvin. Now I can use this R value. All the units are matching. I have liters and torrs, moles, and K is kelvins, which is a temperature unit, and that's the unit I'm looking for anyway. So 62.36, that's the one I'm going to use. 62.36 liters times torr over moles times Kelvin. All right, now you see that I've got it all put in place. Now I just need to solve for T. So this one looks complicated at this point, but all you got to do is divide both sides by both of these things. So I'm going to divide it by 0.0403 moles and 62.36 liters times torr divided by moles times Kelvin. So if I do it on both sides, this cancels out. Okay, that I'm not writing it, but you're dividing by both sides, so you get T by itself. I divided both sides by these two quantities. All right, now I can cancel out units. Moles cancels with moles, numerator, denominator. Liters cancels with liters, numerator, denominator. Torr cancels with torr, numerator, denominator. The only thing left is kelvins. So that's the whole reason I did all those conversions, to show you that. The only thing left is kelvins, and that's what I want. And so how do I calculate? How do I get the number for this? All right, I'm going to pull my calculator again because we get a lot of operation errors for this kind of question. All right, so 780, turn it back on, 780 times 0.969, that's this top, divided by 0.0403, 0.0403. Okay, I'm going to hit divide again by 62.36. Otherwise, you're going to have to put this in brackets. You got to avoid the operation error. So I get 300.75. So my temperature is 300.75 kelvins. But I have to look at significant figures. Everything seems to have 3 sig figs that's measured. This is a definition. So 3 sig figs, so 300, and it's got in there, round up, 301 kelvins. 301 kelvins is my answer. Now, what made that more difficult? That the original units did not show up in the R values that I gave you. So I converted the original units to things that would show up in the R values. So keep that in mind, that your R value, your gas law constant, has to match the R values, so that the R values rather have to match the units in your question so they can cancel out. All right, we're going to go on to the next one, number 6. And I put this one up because I wanted to review collected over water. All right, that means you're going to have to subtract out the water vapor using Dalton's law, okay? Dalton's law, that looks like a P, is, the total pressure is the pressure of the gases. And for us, we're going to just be using the gas of the water and the gas of, the pressure of the water and the pressure of the gas. So we have 530 milliliters volume of a gas collected over water. That means subtract. Super important. At 55 degrees C, that's a temperature, and a pressure of 230 torr. So that's a pressure. What will the new volume be? That's another V at STP. That's another temperature and another pressure. So you see we have 2 volumes, 2 temperatures, 2 pressures. Which formula are we going to use? Volumes, temperatures, and pressures, 2 of them. That means we're going to use the combined gas law. All right, so let's figure out what everything is. A volume of 530 milliliters of a gas collected over water. Temperature is 55 degrees Celsius. Well, first thing we know we got to convert to kelvins. So 55 plus 273 is 328 kelvins. Okay? And the pressure, well, the pressure this time is the pressure of the gas and the water. So the pressure this time is the P total. I got to figure out what P1 is. P1 is going to be the gas plus the pressure of the water. So this is P1, but I don't know what the P1 is. Okay, the total pressure, though, I know. The total pressure was 230 torr right here. So this pressure is PT, not P1. Okay, so we're going to have to figure that out. So 230 torr, the pressure of the gas, which is our P1, plus the pressure of the water. Well, what's the pressure of the water? How do I figure that out? You take the temperature of 55 degrees Celsius and you go look at your water vapor pressure chart. Here it is, water vapor pressure chart. 55 degrees Celsius, there it is. Okay, so here's some pressure, water vapor pressures at that temperature. Now what unit do I need to look at? Well, this one says torr. So is there torr up here? Well, there's not, and I did that on purpose too. There's millimeters of mercury though, and look, 760 torr is 760 millimeters of mercury. So whatever the millimeters of mercury are, I can convert it to torr. So 118 millimeters of mercury. 55 degrees Celsius, 118 millimeters of mercury. All right, so I'm going to convert 118 millimeters of mercury, and really this one doesn't really it's just 760. Torr is 760 millimeters of mercury, so you see everything cancels. It's an easy one. So it's just changing 118 torr. It's just basically changing the unit. So this is 118 torr. Now subtract 230 minus 118 to get the pressure of the gas. I don't know why I put two S's that time. Because I'm thinking about the torr, I guess. So 230 minus 118, and that is 112. 112 torr. And let's see here. What about significant figures? Well, the original one is 230, and so is there a decimal place in that number? I can't see, because I really did mean to put a decimal place there if I didn't. No, I didn't. Shame on me. I want to keep all those significant figures, so I'm going to put a decimal place there. Otherwise, I would have changed this to 100, just 100 torr. We would have to simplify it to 100 torr to only have two decimal places. So, we're adding a significant figure there. So we're going to keep 212. The way I had it before, I would have to convert it down to 110 torr. So this is your P1. That's the real P1. Okay? So your P1 now. Sorry, there we got it right there. P1, that's okay. All right, now let's see. That's your V1, your T1, and your P1. Okay, what about your V2? Well, V2 is the unknown. What is your T2? STP, standard temperature and pressure, so 273 kelvins. What's your P2? Standard pressure. The standard pressure in torr is 760 torr. How do I know? It's 1 atmosphere or anything that equals it, and 760 torr equals it. So now I've got all of it. So P1 V1 over T1, P2 V2 over T2. Add them in there and start doing the math. P1 is 212 torr, or 112 torr. V1 is 530 decimal milliliters. T1 is 328 kelvins. P2 is 760 torr. V2 is my unknown, and T2 is 273 torr, or kelvins. All right, cross multiply and solve. That times that, 112 torr times 530 milliliters times 273 kelvins, okay, equals that times that, 328 kelvins times 760 torr times V2. All right, now how do you solve? You have to divide both sides by 328 and 760. So divide by 328 kelvins and 760 torr on both sides. 328 kelvins and 760 torr. All right, cancel. They cancel to get V2. Kelvins cancel with kelvins. Torr cancels with torr. Milliliters is what's left, and that is a volume unit. So when I put all these numbers in and divide by these two numbers, I get 65.008. Make sure you get that. And I have to count for sig figs. And the things that are not definitions have three significant figures. 3 sig figs here, 3 sig figs here, and I wanted 3 sig figs here. Otherwise it would have been 2. So 1, 2, 3. So 65.0 milliliters is V2. That's your answer. So what made this one a little more difficult? Remembering this right here, guys. Super important. Subtract. Subtracted the water vapor. Where do I get it from? I get it from the reference chart that says water vapor pressure. That's the whole reason you have this chart. Make sure you understand that. Okay, I hope this helps, and I will see you soon.